Hey everybody, welcome to 3.6 absolute value functions. We're going to start with the definition, which a lot of people don't really understand. A lot of people just think anytime you have something in an absolute value, it just comes out positive. Well, there's a reason why, and it only has 3 words in its definition. And that is the distance from 0. That's it. That is the definition. And there is one key word there, the distance. That, my friends, is what causes absolute values to always yield a positive. Because as you hopefully know, distance can never be negative, always positive. Okay? Now we can also define it as what is called a piecewise function. The absolute value as a piecewise function, we know would then have several different things. If we put something into the absolute value, this is our function we're talking about, trying to rewrite it. We know that if we stick in anything positive, the distance from 0 is going to be that same value. So we write x is what our y would be equal to, our function, if x is greater than or equal to 0. That means if you stick in 0, 1, 2, 3, 4, anything positive, then you will get out exactly what you put in. But if you put a negative value in here, such as -3, and that's your input, that's what you chose your x to be, what would you get out for the y value? Well, you'd get what is called the opposite of that value, which of course, for this case, would be +3. So the way that we write this, it's a little bit weird, is -x if we choose an x that is less than 0 or negative. Okay, but a lot of people don't quite understand why it's negative when they know anytime we have an absolute value, it's going to come out positive. This is not saying that it's going to come out negative. It's saying it's going to come out the opposite of a negative, which, yes, yields a positive. Okay, so that is the short notes for this section on absolute values, their definition, how we can rewrite it as 2 pieces, 2 scenarios. Now let's make sure that we remember how to graph these. Now we already went over how to graph these things in general when there was just the absolute value and no other things pertaining to it. So when they asked us to graph, remember those transformations that we were talking about? What did we say would happen for the x? Well, remember the key here is that 0. It's in the definition. So what we want to do is not focus on the outside, but focus on the absolute value itself and try to figure out when that would be equal to 0. And if it's ever just an x plus or minus something, you know to get back to 0, you would have to do the opposite. So remember I told you x is always opposite. Y's are y's. We're going to do what they say. So when we had our original one, 0, 0, 1, 1, 2, 2, -1, 1, -2, 2, this was our generic, we called it the parent graph of the absolute value of x. We're going to take this exact graph and we're just going to shift it right 3 and up 2. That's how quickly I want you guys to be able to graph these eventually. If you need to graph the parent graph quickly and then do the shifts, that's perfectly fine. But I want you to give me that new vertex, so to speak, which is just your shift of 3, 2, which means I know I'm going to take my origin, my vertex of that original graph, and I'm going to shift it right 3 and up 2. That then is going to be my 0, 0, where I'm going to go right and left 1 and up 1. Left and right 2 and up 2. And building that V shape absolute value, it's now going to start here. So I will now go right 1 and left 1 with a Y value of 1. I will go right 2 and left 2 with a Y value of 2 from there. And that should be enough for you to see the graph of this thing is a positive and a negative line. My Y equals X, up 1 over 1, up 1 over 1. And my Y equals negative X, down 1, right 1, down 1, right 1. There is my piecewise function shifted right 3 and up 2. So if you look at part B on this, I wanted to give you one more example of it and throw in one extra piece out in front of our absolute values. And notice with this, not only will we have the shift of, what would it be? -5, -1 for our X and our Y. But we're also going to have, again, since this is not inside with the X, it's going to affect the Y's. And remember, Y's are Y's. We do what it says. We will take all of these original values and we will multiply them by a -2. So instead of going right 1, up 1, we would go right 1, down 2. Left 1, instead of going up 1, we would go down 2. And therefore, not only would this have been flipped, it also will have been shrunk to be more narrow. Okay, so again, pretty easy to do if you comprehend all of those moving parts, those transformations of -5, -1, and what we call this negative out in front, a reflection, and a multiple of 2, which is going to make it twice as fast, either up or in this case, down. So I'll start by shifting 1, 2, 3, 4, 5 to the left and down 1, plotting my point. And then from there, normally I would go right 1 and left 1 and then up 1. But this time my Y's are going to be a multiple of -2. So when I go right 1 and left 1, I will go down 2 tick marks. If I go right 2 and left 2 tick marks, then I will go down, instead of the normal 2, I will be -2 times as big. So 1, 2, 3, 4. 1, 2, 3, 4. And again, you should be able to see the graph of this is going to again be that V shape because it is an absolute value after all. But this time it's a little bit more narrow than the original with the 1 in front. It's going to be twice as fast in the Y direction, and also that reflection from going up to down. Shifted left 5 and down 1. Okay, I would really like you guys to be able to graph these as quickly and easily as possible. You don't need to use a T-chart, but if you'd like to, find out what would give you 0 and do a couple above and a couple below that to find your Y values, and then graph each and every one of those points. A minimum of 5 is preferable, and we're done. Okay, so let's move on to other types. Let's see if you can work backwards. What if, instead of me giving you the equation and asking you to graph, what if I explained what the graph looked like and I asked you to provide the equation? So this one asks us to write the equation of, well, they're telling us it's an absolute value function. So right then and there, I know it's going to have that straight brackets around it, and it's horizontally shifted. meaning left and right, which means x-axis. It's going to have an effect on the x. And it's left 2 units. It's flipped vertically, meaning we're going to have one of those negative reflections, and also shifted vertically up 3 units. So what do we have here? Well, we know we have some function, an absolute value function, where things could be happening on the outside, things could be happening to the x, and things could be happening to the y. And hopefully, as you guys saw, this told us that we are dealing with the absolute values. And we have 1, 2, 3 things that would be done to it. And what are those things? Well, first it said horizontally shifted, left 2 units. Well, remember, because it's the x, we're going to do the opposite. And that means we're going to put +2 here in order to actually shift it left 2 units. It's vertically flipped. Now, it didn't say anything about it being more narrow or more wide. So vertically flipped, meaning we will then have a negative. You can put the 1 if you want, but a negative on the outside. And lastly, vertically shifted up 3 units. Now remember, y's are y's. We do what they say. So that is going to be up 3. And that, my friends, is working backwards when they give us an explanation or even a graph and ask us to provide the function or equation of the function. Okay? So how do we then solve an equation with an absolute value in it? Not just talk about the looks of them like we did here and there and then working backwards, but how do we actually solve one of these equations for x given some y value? Well, it's pretty simple. For the absolute value, make a v, and that tells you you got 2 steps. The first is we want to make sure that we isolate the absolute value, get it by itself, just like we've been taught and have done for many, many years in math, but usually for a variable. Now we want to make sure that we get that whole absolute value by itself, because our goal really is to get rid of it. We don't know how to solve equations with absolute values in them. So we're going to get it by itself, and then we're going to apply the definition, which is the distance from 0, which means we will have a positive and a negative case. Because I know the distance from 0, let's say they have this equation where they want us to figure out when this would be equal to 5. Well, I know that I could put in place of this x a 5, and I'll definitely be a distance from 0 of 5. Or I could put in a -5 for x, and that would also be a distance from 0 of 5. So when doing these, first we isolate. First step tells you what to do. Get that one absolute value by itself. And then step 2 tells you what to do. You do the 2 cases, the positive distance from 0 and the negative distance from 0. Pretty simple. So let's try it. Let's do an example. What if I gave you this function? Obviously, it's an absolute value function, and I wanted you to find all the x's where f of x is equal to 0. In other words, they're telling you y is equal to 0. Graphically, that means we're somewhere here, either here for this x or this x or this x or whatever. Let y equal 0. Change the f of x to what it's equal to. Then that means we're dealing with this. 2x minus 1 in my absolute value minus 3 is equal to 0. So step 1, get it by itself. That would require us to add 3 to both sides. Then, now that I have my absolute value by itself, step 2, do your two cases. Take whatever's inside of there, happens to be a 2x minus 1, and set it equal to the positive case of the distance that we are trying to achieve from 0, and set it equal to the negative case. Now you got two equations that you should know how to solve. These are called linear equations. We've been doing this for a very long time, and you're done. I like to solve them simultaneously because I know all of this was going to be the same. And that's what I'm trying to get, is that x by itself. So by adding 1 to both sides of both equations, I now have 2x on this one equals 4. On this one equals negative 2. Then my last step would be to divide by 2 to both sides of both equations to get my 1x equals 2 and my 1x equals negative 1. And guys, how do you know if you've done this correctly? You simply plug it into the original one at a time for x, work this out to make sure that you get whatever value they give you, in this case, a 0. All right, that's it for this section. We'll go ahead and move on to the next here in the next video. So go ahead and stay tuned for that. All right, we're back for another section, the last section of this chapter, 3.7, titled Inverse Functions. If you guys remember, the inverse is one of the big 3 concepts in all of mathematics that is the most important. Multiplying by 1, solving equations, and the inverse, which is what we use to do a lot of the solving. Okay, so what is the inverse? Well, inverse is just a fancy math term for the reverse. In other words, when you have addition, how do you undo that? Well, the reverse of adding is subtracting, multiplying, dividing, squaring, square rooting, logarithms, exponents, exponential, right? All of that stuff in math that we've learned over the years, we've always had to make sure that we can undo it. And that is called the inverse. Okay? So when we talked about the inputs or the domain and the outputs and range, then what does that mean if we're doing the reverse or the inverse of these things? They too would be flip-flopped or reversed. So if you know the domain and range of a function and they ask you to find the inverse and their domain and range, then just flip-flop them, and you know the domain of the original is going to be the range of the inverse function. Okay, so as you can see in the next line here, if we find the inverse of a function and we want to make sure that it also is a function, then we got to make sure that it is what is called a one-to-one function. Meaning that if I put one thing in, I only get one thing out. That's a function. But if I go the reverse direction, then for that one output, I need to make sure that it maps to one and only one input. So that one-to-oneness for a function means that one-to-one, one-to-one in both directions. Okay? And if we have a graph, we can very quickly and easily check to see if it's one-to-one function by using a little thing called the horizontal line test. Now remember, we used the vertical line test to see for each and every x, did it only give me one y value? Well then, to do the reverse, we would use the horizontal line test to see if each and every y only mapped to one x. Pretty simple if you really think about it. Hopefully it makes sense. All right. So as you can see, because that's so simple compared to trying to figure it out in an alternative way, it's in our best interest to be able to recall and visualize all of those graphs that we talked about last time. Okay, those parent graphs or toolkit graphs, all the original graphs. Because then you should be able to look at an absolute value and you know it's a function, but is it a one-to-one function? No. Can we make it a one-to-one function? Yes. We could simply get rid of half of it, and now it would pass and be a one-to-one function. We can restrict the parts of it that we look at so that we can find the inverse of things. Okay? So the way that we denote inverse, I don't know if you guys remember, is this little power of -1. Now remember the -1 power, when we had x to say the -2, that meant that we had to take this negative and move it to the opposite side of our fraction to be, there's always something up there. So in this case, there's 1 x to the -2. So now I'd have 1 over x to the +2, but in the denominator. We called it the reciprocal when we had negative exponents. However, we're going to reuse this symbol of -1. We're also going to let it be the inverse symbol. So how do we know when we should be flipping things and doing the reciprocal for those -1s, or it's referring to the inverse? Well, to make sure that you guys understand, since we're dealing with the function, we're going to put it after the f and not after the x. Because if we had this, that then would be pertaining to the x, not the inverse of a function. That would actually look like this. Okay, so if you ever see that little -1 power, remember, if it's to a function, it's represented the inverse of it. But if it ever is a negative exponent to a variable or an actual number, then you're going to have to do the reciprocal like we talked about. All right, and I do want you to keep in mind that not all functions have inverses. Those are the ones that fail that horizontal line test. All right, so if we are given two functions, say f of x and g of x, and we wanted to test if they are inverses of each other, then what we're going to have to do is a little composition of functions that we talked about a little bit ago. F of g of x. If they are indeed inverses of each other, then what's going to happen? Well, they're going to undo one another, and whatever you put in, you will get out. And it shouldn't matter if you do f of g of x or g of f of x. They should still undo one another if they are truly inverses. So again, whatever you put in, you will get out. So we are looking to get out whatever we put in. And by doing the composition, f of g and then g of f, if we get out of that, they undo one another completely. And we get out exactly what we put in, we know that they are inverses of one another. Let's try an example of that. Let's say we have this as our f function and this as our g function. Now, do they at first glance look like inverses of each other? Doesn't look like it really, right? Now, you can see that 1 is being subtracted by 1 to the x and then cubed. But the other, the x is being cube rooted and then added by 1. But remember, the inverse is the reverse. So this definition up here states that if either of those statements are true, f of g or g of f, then both should be true. So if we want to see if g is equal to the inverse of f, then what are we going to be doing? We will plug in are f of g of x. Now again, according to this, it says that you can do either f of g or g of f, and it will suffice. Okay, so for this, we're trying to see if g is equal to the inverse of f. So I'm going to put g inside of f. And if you remember from when we were doing these in the previous video, f of something is equal to, they already told me, f of something is equal to that thing minus 1 cubed. And unfortunately, they didn't want us to just plug in an x. They wanted us to plug in an entire other function, g of x, which is cube root of x plus 1. So then I will replace everywhere there was an x, that cube root of x plus 1. Now I'll do my order of operations, which says parentheses, nothing doing there, so I can really just get rid of them. And that means then I will have the cube root of x plus 1 minus 1. Now I'll do the next outer set of parentheses. What can I do in here? Well, hopefully you can see 1 and negative 1 cancel out. So the only thing left now is the cube root of x inside of the parentheses that is being cubed. And you know that adding and subtracting the same number, inverse operations. They undo one another. Same thing with cubing and cube rooting. They will undo one another. And therefore, what we get out is just what we put in. And therefore, we can say with confidence that yes, they are inverses. Okay, if you don't believe me, go ahead and try the other direction. That's fine. You can do g of f of x to ensure that you do get the x out. Definitely safe to do both. Okay, but not necessary. If either one of them is false, then they're both false. They're not going to be inverses. Okay, that's called a counterexample. So, what about those domain and ranges that we talked about? Well, remember, if you have the range of the original function, then the domain of the inverse is going to be equivalent, and vice versa. The domain of the original would therefore be the range of the inverse. Again, inverse, fancy math term for reverse. Okay? So, what if I gave you an example geometrically via a graph, and I asked you to evaluate, find some things that I want to know, like g of 3. Well, I'm telling you that this is the g of x function. And since I replaced the x with a 3, you know to go to the x and go either up or down, in this case up, until you found your y value. So you know that g of 3 is equal to 1. But I'm also asking you to find g inverse of 3. And you're looking at this and you're like, hey, this is the g function, not the inverse. Do I have to go and find the inverse of this? No, you need to recognize that if I was to write down what I know this stuff is, g of x is equal to a y value. What if I did the inverse? That's the same as writing this is my x and this is my y. This is the point 3, 1, isn't it? Well, then what would the inverse be? If you wanted to rewrite it, g inverse, this is now going to be your y. They want to know the x. So when we reverse the order, that's when we see the inverse symbol. And you need to know that this is no longer the x there. Because of this, that is now the y value. Again, because of the inverse. So I'm looking where the y is 3, what would give me the x? So rather than starting on the x-axis and going up until I hit my y value, now I'm going to start on the y-axis at 3, and I'm going to go, in this case, right until I hit my x value, which this time would be 5. Okay, so a little tricky there. You need to recognize that what they gave me was g of x as my graph, and I know if this is the x, then I go to it until I find my y. But when they give me the inverse, they have reversed the x and the y values in the original form that we're used to seeing. And that's a little weird, and therefore it becomes a little challenging. It's different until you get the hang of it. Okay? So when you see the inverse, know that your order pair is reversed. They're now looking for the x for the inverse, and they're going to give you the y value. Okay, so just again, be careful with that. It's a pretty easy concept, but it's also easy to get mixed up. All right. So now that we've seen the geometric side, let's take a look at how we would find the inverse function given an equation and doing it algebraically. Okay. Again, there's really only 2 steps. I try to make things as simple as possible to find the inverse of a function. There is that one important caveat, and that is, in order to find the inverse, it has to be a what kind of function? Hopefully you said 1-to-1, because otherwise it doesn't function very well. Okay, you may have been in a relationship like that. Okay, but again, you want to make sure that your function is 1-to-1 in order to find the inverse. And once you verify that, then you can go on and do these 2 steps on how to find the inverse. Again, has to be a 1-to-1 function. Narrowed it down to 2 simple steps. Okay, if you're going to be finding the inverse, you're going to do the inverse, and that means you're going to switch, reverse all the x's and y's. Anywhere you see an x, you're going to replace it with a y. Anywhere you saw a y, sometimes they write it as f of x or g of x, you're going to replace that with the x. Okay, and then once you've done the reverse of all the x's and y's, now we want to get our function the way that we're used to seeing it, with that y, and I call it a new y value, so that you can see exactly the way and form that we're used to graphing things. Okay, so pretty simple, 2 steps. Let's see if we can do this and put them all together with this example here. Part A, I want you to find the inverse. Part B, I want you to state the domain and range of the inverse. And then I want you to graph both f of x and its inverse on the same set of axes. Okay, I also put on here, be sure to state any domain restrictions if needed. Sometimes we will need to do that to ensure it's a 1-to-1 function and it works for both the original and, more importantly, the inverse. Okay, now you all should be able to look at this and know exactly what it looks like. So I'm not going to go A, B, C order. I'm going to actually graph the original function right now. And should you all know what the square root looks like? Well, it kind of looks like a square root. Remember, it's that half of a parabola on its side, but we got some stuff being added and subtracted to it. So we're going to have some shifting, some translations going on to this square root function. So you should already know that the look of this is that 0, 0, 1, 1, 4, the square root of that is 2. 9, the square root of that is 3, and so on. That's the original look of this graph. Okay, and if that's the original look of this graph, you need to know how this subtle variations of subtracting 4 to the x and adding 2 to the y, whether they put it at the beginning like they did or at the end, you need to know it's not being done to the x, so it's going to affect the y. This is going to yield a shift of this graph by a new quote-unquote vertex of, remember, x's we do opposite, try to zero that out, and then y's are y's, because if we zero that out, that means the y will be equal to that. So 4, 2. Which means I know all I'm going to do to graph this is take this original graph, because nothing else has changed from the square root function other than the 4 and the 2, if you notice. And I will take this quote-unquote vertex and I will shift it over 4, up 2. Plot my point, go over 1, up 1, over 4, up 2. And that's enough for my graph. That's it. That's what I'm going to do for my shift. So I will start by going 4, 2. And once I have that vertex, then I knew that this was going to be my new x-axis, my new origin. And I would go over 1, square root of that is 1. Over 4, square root of that is 2. 9, 3. And boom, draw my graph and I'm done. So over 1, total of 4. So over 1, up 1, over 4, I know the square root of that is 2. And there's my graph. Now remember, that's my original function they called f of x. So should you be able to give me the domain and range of that original function? Absolutely. Remember the domain, we start from left to right, smallest to biggest on our number line, and then smallest to biggest on our other number line going vertically in the y direction. So when do I start hitting my x values? Well, not until that shift of 4. And is it included? Absolutely. So 4, and it goes to infinity, which we said never include because it's an idea, not something that we can actually graph and touch. Now the range, again, be careful, smallest to biggest, we don't start until we get to that other shift in the y direction. And again, that is an included value because it's a solid dot. So I will start and include 2, and this one, even though it's more subtle, continually goes up until there is no end, infinity. Now remember, if this is for my original function, you should already then therefore be able to tell me what the domain and range are for the inverse function. What's the domain of the inverse? It's just the range of the original. So that means this is now going to be 2 to infinity, and the domain of the original will flip-flop to be my range. So this one will now be 4 to infinity. So if you notice, we've already answered part B, the domain and range of the inverse function. We got that without even having to find the inverse function or graph the inverse function. We've also graphed the original. We need to graph the inverse, and I'll talk about how to do that right after I show you how to find the inverse of our original function here. Now I don't like the f of x, so I'm going to just for now replace it with y because it's easier to write than f of x. And if you remember, y equals 2 plus the square root of x minus 4 is my original function. The first step we do to find the inverse is reverse our x and our y. So the only things that will change are those. Everything else stays the same. But although we could be done here, we don't like to graph this. I don't know if that's a function because I'm not used to seeing it as x equals. We're used to seeing it as f of x or y equals. So step 2 is to isolate that y. Get that new y by itself. You guys know how to solve an equation by now, so let's do it real quick. And as you can see, we end up with this graph. Just don't forget, we replace the original f of x up here with the y. They're going to want you to replace it back so that they know that we're still talking about the same thing. So I'm going to have to just rewrite this as f to the -1 of x, or f inverse of x. However, notice, hopefully, you know the graph of this. If I got rid of the adding and subtracting parts, it's just an x squared function. And you should know x squareds are parabolas. And parabolas, whether it's shifted right to and up 4 or just at the origin, we know that those are not one-to-one functions. So, although this is my answer to part A, remember I put, make sure that if there are any restrictions needed to make it a one-to-one function, that happens. And let me show you by demonstrating how to graph an inverse function when you have an original function. If you recall, there is one thing that we can graph very easily that does not change when you do the inverse. And that was the graph y equals x. Because when I switch x and y, I have the exact same thing. It's not going to look any different like this one does compared to its original. Okay, when you take the inverse of, they call this the identity because the x and the y have to be identical. 0, 0, 1, 1, 2, 2, 3, 3, -1, -1. They're all the same. Then this, my friends, is your mirror to get your inverse function to that. And if you remember, the inverse is the reverse. And if I know that this point right here is 4, 2, and this point right here is 5, 3, and this point right here was 9, 4, then what does that mean the inverse of all of those ordered pairs would be? It would just be the reverse, flip-flopped. So I know the graph of this is going to include, if this is my original in this shape, 4, 2, then the inverse is going to include 2, 4. 5, 3 will flip-flop to be 3, 5. And if you notice, when I graph this, I get my beautiful butterfly with that same look on the other side of this everywhere. But again, notice we already had said that we would be able to know the domain and range of it. The domain we said should be the range, and the range should be the domain of the original. Well, if you look, let's make sure, when do I start hitting the x's in my other one? Not until 2 and everything to the right eventually. For my range, I don't start hitting until 4. And of course, to positive infinity. So whether you graph it first, or if you have the original one and you already know it in your head and you know these things, then you can give me that without finding and or graphing the inverse. Okay? Lots of stuff going on there. Hopefully you guys were able to follow it all. We can definitely practice that more, but remember to find the inverse, switch your x's and your y's, do the reverse, and then second step, solve for that new y. So it's in the form that we're used to being able to know and graph. To find the domain and range, you can use the original function or the inverse function to find them. Just make sure that you give them the domain and range of what they requested. And then to graph the inverse of a function, you merely just mirror it about and always the line y equals x. And again, it will always be that because it is itself when we do the inverse. Okay? So make sure that you notice if this is going to be an inverse one-to-one function, then we would have had to have said that we got to restrict, because technically this is a parabola and we would have the other half of it. So to make sure that it matches up with what we had originally, we're going to have to restrict this parabola to only having x's greater than or equal to 2. That then, my friends, would get rid of the other half of this that we technically would have been graphing. All right. I hope that helps. Good luck in your journey mastering all of this material. Until next time, Alan, signing off.